It's called the free body force diagram, mentioned in a previous video. And because I am studying the box in this Newton's second law problem, this free body is meant to be the box. So the box you draw as a dot, that's the box right there, and then on the free box, the free body, I'm going to add the forces. So I'm going to diagram the forces acting on the box. There's only two. Here they are. One of the forces on the box is the normal force by the table. The table's underneath the box, and the table's going to be pushing up on the box. Here it is. Normal force on the box by the table. The other force that's acting upon our little box dot, our free box, is the weight force. That one points down. So I'll just put the weight of the box, where B is just an abbreviation for all that stuff sitting there. An interesting thing is I don't know which of these arrows to make bigger. Honestly, it doesn't matter. It's just a diagram. You might happen to know that this force is bigger than that one, and so you diagrammatically could make this arrow bigger than that arrow. But it doesn't matter. It's more of just record keeping or a summarization or a memory tool to fill in all of this forces acting on the box. Here are two, and there they are in the net force statement. What is really important, though, is the fact that we put these two arrows opposite each other, at least in the same direction or same spatial dimension, because this elevator and all the things associated with it, this is a one-dimensional problem. And so really, even though I'm drawing arrows and stuff in a two-dimensional piece of paper, this is a one-dimensional problem. And these two arrows point, they happen to point anti-parallel. In this particular case, the weight force is down and the table pushes up on the box. But the point is they are in the same line. Okay, so this is a one-dimensional problem, really. All right, so my unknown is here, and I can solve for it algebraically. Algebraically, it says that the normal force on the box, which is the answer by the table, that's the answer to at least the first part of my problem effort. It's equal to this thing minus this thing. It's just a little bit of algebra with vectors. So there's the weight, or I mean, this is the F net equals to ma part. So this is mass of the box times the acceleration of the box. The mass of the box is right here, and the acceleration of the box is right there. So I know all the details of this. There it is. But I have to subtract. So minus the weight force of the box, or the weight force acting on the box, excuse me. So this minus sign is super important, and let me show you why. Let's choose up to be the positive direction. Then we're going to say that the normal force on the box by the table is equal to, so if up is positive, then here's the mass of the box, here's the the mass of the box and the acceleration A of the box here. So 3 times 10 is 30. Meters per second squared times the kilogram is the Newton. And the acceleration vector is up, but up is positive, so I'm going to put a positive sign in here. So all of this thing is positive 30 newtons. And then I'm going to explicitly, there is a minus sign there, so I'm going to put it there. And in parentheses, I've got to be really careful. This you have to be careful, so I'm going to draw an exclamation point. In parentheses, I'm going to put the value of the weight force against this positive direction arrow. So I know that the weight force is the mass of the box, 10 kilograms, times the acceleration due to gravity on the Earth, which is that downwards value, 9.8 meters per second squared. So 10 times 9.8 is, so I'll put it over here. So the weight of the box is 98 newtons downwards. So that means that when I put in the weight of the box against this upwards being positive arrow, this down means this is a negative number in this coordinate system choice. So I have to put in a minus 98 newtons. This is really important because look, there's two minus signs. The outer minus sign came from earlier algebra. You don't get to negotiate that one. The inner minus sign comes from the choice of coordinate system. And once you choose a coordinate system direction, what that did was it chose that sign. It's going to choose how we understand the sign of the answer, but it also dictated our what we had to put here. And a minus minus is a plus, and so it's 30 plus 98. It's 128 newtons with an overall plus. That is the normal force points up. So the normal force on the box by the table is 128 newtons upwards. And here is an answer, at least to the first part of our problems. So let me continue on the next page. So I'm going to, just to give you a heads up on what's about to happen, so I've solved this one fully. I gave you a coordinate system. I told you about arrows and vectors. I exploited the fact that we're in one dimension to kind of remove the direction, or at least the explicit arrows, and instead we're keeping track of the SIGNs, the signs of things, against a chosen orientation of the coordinate system. And I was fully able to solve at least the first part. So the next page, on this next blank piece of paper, I'm going to show you what's involved in getting this, but I'm not going to solve it fully, but I'm going to point out some interesting new things that show up in this analysis for this problem versus that one. So we're wondering at this point, what is the normal force acting on the table by the elevator? So that's our new problem. So I'm going to put equals, what the heck is that? So this is my goal on this piece of paper, or at least, yeah. So normal force on the table by the elevator. Here is the table. The elevator is underneath the table. The elevator touches the table on the bottom side. So the elevator is going to be pushing up. So on the table upwards by the elevator, which sits below. So this, we expect it to be an upwards arrow. All right. So just as a, maybe so that you can have it over here as I write, don't forget that our problem is a table with a box and a rope. So the rope, the box, the table, the elevator. Okay. So, so check, this is interesting. This is about the table. So I'm going to start off this time by drawing a free body force diagram where the body that I want to start with free is actually the table. So I'll draw a dot for the table, just like I drew for the box. So there was the box there, I had two forces on it. But in the case of the table, here's the table. The elevator is going to push up on the table. So this is normal force on the table by the elevator, right? So that's one of them. But on the table, the box is sitting on the table. And if you think about it, if the elevator really accelerated upward quickly, that box would press so hard down in the table, it might bend the table, or the table could break. So the point is that actually, I know that there is a force downwards on the table because the box is pushing down on it. So I'm going to draw that. This is the normal force, or contact force, acting on the table. In this free body force diagram, I'm only allowed to draw forces that act on the table. And in this case, it's not by the rope or anything else, or the elevator. It's on the table because of the box. It's on the table by the box. Okay, and we're not done yet, because remember the table has a mass. The mass of the table was 20 kilograms. The acceleration due to gravity in the background is 9.8 meters per second squared down. So here are the details that lead me to remember that actually there is another force acting on the table. It is the weight force, and I'm just going to tack it on to the bottom of this arrow. That is this arrow and the weight force arrow. This is the weight of the table. They are acting together downwards, and there is an oppositional force upwards, the normal force on the table by the elevator. So this is my complete free body force diagram. There are only three forces acting on the table. The acceleration of the table is, again, 3 meters per second squared. So if I write down Newton's second law, the net force on the table, it's equal to, here's the free body force diagram. So watch this. This is an important step. The normal force on the table by the elevator plus the normal force on the table by the box plus the weight force on the table. Big deal here is when I calculate the net force, there is only plus signs. I know that these two forces point downwards relative to that one. So in a sense, these have negativeness compared to this positiveness. But when I do the net force is defined as a summation. That is, when you have vectors here, it really is only plus signs because that is a sigma for sum. It's not a difference.